Welcome to the Explainer. So, have you ever wondered how we actually made the leap from AI that could barely process one single picture to models that read entire web pages, seamlessly jumping back and forth between text and images? Well, today we are decoding DeepMind's monumental 2022 breakthrough, Flamingo. This was truly the dawn of few-shot vision language models.
To keep things crystal clear, here's our roadmap for today. We'll start with the single image problem, then see how Flamingo enters the chat. From there, we'll break down the Perceiver Resampler funnel, the gated cross-attention bridge, explore the magic of few-shot learning, and finally, wrap up with Flamingo's lasting legacy.
All right, Part 1, the single image problem and early VLM limitations. Let's quickly look at the major obstacle earlier AI models faced in our messy, multimodal world.
So, how do you teach an AI to read a conversational stream of mixed text and images? Before Flamingo came along, if you wanted an AI to look at a picture and talk about it, you were dealing with a really strict constraint. Older models like Blip2 fed just a single image into the AI at the very beginning of the prompt. Now that works beautifully if you literally just have one picture. But parsing a natural conversational stream, like a blog post that goes, here's image A, caption it, now here's image B, caption it, that was a massive headache. The AI's attention mechanism just couldn't juggle that chaotic mix of text and image tokens all at once. It's kind of like asking someone to read a comic book, but only letting them look at the cover.
The shift here is absolutely crucial. You have that rigid single-image setup of Blip2 on one hand, and then you have Flamingo, which was engineered from the ground up to natively support a completely free-flowing, arbitrarily interleaved sequence of images and text. It was specifically built to consume media exactly the way you and I do online.
Moving to Part 2, Flamingo enters the chat. Let's look at DeepMind's solution to this seemingly impossible task.
The secret sauce here really begins with treating the core language model like a protected sanctuary. DeepMind started with their massive Chinchilla 70 billion parameter large language model. But here's the brilliant trick. They kept it entirely frozen, meaning during the visual training process, the underlying text model's weights remained completely untouched. Think of the model's brain like Han Solo frozen in carbonite. Its pristine, highly capable text reasoning was perfectly preserved with zero risk of being overwritten or ruined by the new experimental image data.
But wait, if the brain is frozen, how do you actually get the images inside? That brings us to Part 3, the Perceiver Resampler funnel and standardizing images. What's really fascinating here is how Flamingo handles the sheer chaos of different image sizes. Because, when you feed images into a vision transformer, a small image creates a few data patches, and a large, high-res image creates a ton. If you just dumped all those variable patches directly into that frozen LLM, it would get completely overwhelmed. So Flamingo solves this using a Perceiver Resampler to standardize all that visual data before it ever even reaches the text brain. You can really think of this resampler like a giant funnel. In Step 1, a fixed number of learnable latent queries attend to whatever variable number of patches you happen to throw at it. Whether you feed it 196 patches from a tiny image or 900 patches from a massive one, Step 2 guarantees it always perfectly outputs exactly 64 neat, standardized visual tokens. It's honestly an incredibly elegant way to keep the data stream predictable, which saves engineers a massive amount of computing headaches.
Which leads into Part 4, the gated cross-attention bridge. So we've standardized the images, but how do we actually merge them into the text stream without completely breaking that frozen LLM?
Well, DeepMind built bridges. Specifically, they inserted brand new gated cross-attention layers between every 4 layers of the existing frozen LLM. These layers act as literal bridges, allowing the text tokens to cross-attend to the new visual tokens. But remember, the base LLM is perfectly tuned for text right now. If you were to suddenly flood it with loud, random visual noise at the very start of training, the model would suffer what's called catastrophic forgetting and essentially just collapse.
So the absolutely crucial point here is the number 0, the mathematical gate, specifically a tanh function, controlling the visual data, initializes at exactly 0. This means at step 0 of training, the visual bridge is completely closed. The model is behaving exactly like a perfect text-only Chinchilla LLM. Then as training progresses, this learned gate slowly opens. It acts exactly like a water valve, smoothly introducing that visual information without shocking the system.
And to keep things strictly orderly inside those interleaved prompts, Flamingo uses causal masking. Basically, a text token is mathematically restricted so it only ever sees the image immediately preceding it.
So if your prompt is image A, caption A, image B, caption B, the text in caption B absolutely cannot accidentally see image C from the future, and it doesn't get confused by looking all the way back at image A either. It focuses right where it needs to.
Okay, part 5, the magic of few-shot and in-context learning. Let's see how all of this architecture builds up to an absolutely incredible capability.
Because that massive 70 billion parameter text brain was kept completely frozen and safe behind those zero-initialized gates, its remarkable ability to learn from context carried over directly to the visual world. Meaning you could now use few-shot in-context learning for images. You can format a prompt just by showing the model 3 different pictures, each followed by a caption of your choosing, and then
When you hand it a 4th, brand new image, the model immediately catches onto the pattern and captions it perfectly. Honestly, when I first read this part of the paper, it blew my mind. No gradient steps. You literally do not have to retrain or fine-tune the model on a massive dataset to teach it a new task. You just show it a few examples right there in the prompt, and it instantly figures it out. This was a monumental leap forward for AI flexibility. Which brings us to our final section, Part 6, Flamingo's Lasting Legacy. Because this definitely wasn't just some cool isolated experiment. Looking at the stats, the leap from earlier models like Blip 2 is just staggering. While Blip 2 is amazing for single image tasks on a tight budget, training only 188 million parameters, Flamingo completely traded that budget efficiency for massive scale. By training around 10 billion parameters just in its cross-attention layers, Flamingo unlocked strong few-shot reasoning and true interleaved mastery. It proved for sure that scale and architecture could actually solve the multimodal puzzle.
And the DNA of this 2022 paper lives on literally everywhere today. It birthed direct open-source reproductions like OpenFlamingo and Otter. It heavily influenced Hugging Face's incredibly popular Idefics lineage. And perhaps most notably, it conceptually paved the way for massive modern models like Google's Gemini. Meaning the very AI you might be using on your phone right now owes a massive debt to this specific architecture.
But, of course, the industry moves incredibly fast. Today, many frontier models are shifting toward early fusion, mixing text and images together right from the very first layer instead of bridging them later on. So it leaves us with a really fascinating question. As architectures continue to evolve, will the elegant closed water valve of Flamingo's gated cross-attention remain the gold standard whenever we need to protect a frozen LLM? What do you think is the best way to teach an AI to see? I highly encourage you to dive into the original DeepMind paper to explore the math and the magic even further. Thanks for checking out this explainer with me, and keep learning.